So in the first question, we need to find the domain. So we have a natural logarithm. So that means that the argument must be positive. So we basically said we do an inequality with x plus y plus 1 greater than 0, and that ends up being y greater than minus x and minus 1. Which are above the line. Then for the limit of xy as they approach 1 and 1 of this function, well, we first solve it as a function of f of 1 and 1, and we compute that, we end up getting a real number, so it's 2 over 3. In this case, we have the same function as before, but as the limit approaches 0, 0, and we need to try with different paths, like setting y equals 0, or path 2 setting y equals x, and comparing the two paths we get different answers. So that means that the limit does not exist. So here we can compute the gradient. We can compute the gradient of f. We end up getting computing the gradient and having plugged in the numbers given the points. We get the normal vector to the tangent plane is 4, minus 4, and minus 6. So then we use the point normal form of a plane, and we set it equal to 0. And then we simplify the plane equation. We end up with 2x minus 2y minus 3c z equals 3. So this problem we could rewrite it as a level surface, then compute the gradient. So we take the partial derivatives, and we end up evaluating the point given. So we end up with a normal vector n equals 1 to 5, 1 comma 2 comma 5. And then we set the parametric equations of the normal line. We end up with x equals 2 plus t, y equals minus 1 plus 2t, and z equals 0 plus 5t. So proceeds. Find the directional derivative of f at a given point in the indicated direction. So in this case, well, we need to find the direction vector and unit vector. Then we solve for the gradient of f. We evaluate the gradient at the point given, which is minus 2 and 0. And we then set the directional derivative formula. So we end up with du f of minus 2, 0. Computing with the plugged in numbers, we end up with minus 4 over 5. Here we need to find the local minimum of the function. So we first find the critical points, which basically we set the partial derivative. We solve for the partial derivative with respect to x, with respect to y. We set that equal to 0. Then we plug in the numbers of the solutions. So we plug one of the equations into the other, basically. We have the critical points of as minus 4 and 1. And we check if it's a minimum. So we check that with using the equation d equals fxx times fyy minus fxy squared, which is equal to 3. And then in fxx is equal to 2, which is greater than 0. So we have a critical point, which is a local minimum. And we evaluate f at minus 4 and 1. So evaluating f at minus 4 and 1, we end up getting minus 11. So So here is, we should do basically the same in terms of finding critical points, in this case in the interior of the shape. We substitute one of the equations into the other, which gives f equals 4 at 1, 2. We then need to check the boundaries. And we end up comparing all the candidates at also the given points. Where we end up with an absolute maximum of 4 at 1 and 2, at the point 1 and 2, and an absolute minimum of minus 64 at 2 and 4. So here we need to go ahead with the same process as I explained the last two exercises. Finding critical points, or in this case we can use symmetry. We end up getting the candidates as plus minus 1 comma plus minus 1 comma plus minus 1. So we end up getting the absolute maximum as 1 and the absolute minimum as minus 1. So here what we need to focus is that if f has a continuous second order partial derivatives, then using Clairaut's theorem, we should end up getting f of x, y, x and y is equal to f, the partial derivative of fx yx of xy. So by computing the two partials and comparing both of them, we end up getting 2y, and for the other one f of yx is 1, so they are different. So then this is false. So here what can say it's true because the notation is correct. Well, here we should think in terms of directional derivatives, and we should take any unit vector and apply the chain rule, let's say for g of 0, equals the gradient of f of a and b, and doing dot product with that to u, then setting that equals to 0. So we end up finding out that the only vector that has dot product 0 with every vector u is basically the 0 vector itself. So then the statement is true. So here we should first compute the partial derivatives with respect to x and with respect to y. Um, we end up finding out that the gradient of f of x and y, well, it should be equal to 0 comma 1 over y. So maybe there is a problem with the notation. So the statement is false. Well, here we should recall the second partial derivative test. Analyze when f has a saddle point, or local minimum or local maximum, and compare this with the condition in the statement. Where when we have a saddle point, this less than 0. So the condition that we are given is where d is less than 0. So we can say that the statement is true. Okay. So here we should first compute the gradient. Then we should bound the gradient's magnitude. We end up with magnitude of the gradient of f of xy is less equal than square root of 2. If we combine this with the given inequality, we end up with exactly this same statement. So the bound is true, basically.